All right, guys, so we are moving on to talk about limits and continuity. We've touched on continuity a little bit before. I think you know the general idea, but we're going to do some formal definitions with that. And involved with the definition for continuity is limits. So we have to do both of those together. So first, looking at this graph on the left here, do you think that's a continuous graph or does it have a discontinuity? How do you know that? There's an open circle, right? Do you remember what that discontinuity was called? What kind? That's a hole. Yes, so we've got a hole in the middle of that. I'm going to call this like A on the x-axis. So I would say f of A is undefined. It is a hole, okay? Okay, now looking at this graph again, we'll call that A. What do you think? Does that graph have a discontinuity?
Yes.
Yes, it still has a hole in the middle of the graph, right? Is f of A undefined, though? No. Okay, so that's just something to be aware of. So f of A is defined here. So it is defined. But there still is a discontinuity. There is still... Okay, so we have to be good at identifying if a function is defined or not at a certain x value. And then the other part we have to start thinking about is the limit. All right, so we need to figure out what a limit is. So let me show you the notation first. So the definition here, the way we write it, let me write it and say it, and then you guys can copy it down, okay? So this is the limit of f of x as x approaches A equals whatever it equals. We'll say L in this case, okay? So I'll give you a minute to jot it down. So what this limit is telling you, it's saying as x approaches A. So as we squeeze in on this x value of A, so we're looking at it from both sides, what y value is our graph approaching? Not what does it necessarily equal at that point, but what is it getting really, 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 really close to from either side? So you can even think, like if I put a little person on my graph here, and they approach the x value of A from one side, and they approach it from the other side. Do you guys see how L is the y value that that graph is approaching? That's what you're looking for. What y value are these people approaching? Okay, as you squeeze in from both sides of your graph. So we're going to look at it graphically. You can also see it in the table part of a calculator. So as I look at this table right in here, as my x values get closer to 3 from either side, so like I'm squeezing in on it, do you guys see how the y values are approaching 6? Okay? That's what we're talking about. What y value is it getting close to? So let's do a few of these with actual equations instead of a's and l's. All right, let me give you the equation x plus 3. So y sub 1 equals x plus 3. Let's make a graph of that. How do I graph y equals x plus 3? Yeah. Yep, y-intercept is at 3. And then I know the slope is up 1 over 1. There's my lovely line.
You always approach both sides of the line towards A.
Good question. So it depends on how the limit is written. We'll get further into this and we'll talk about left-hand and right-hand limits. So if it says like a left-hand limit, then you only approach from the left. If it says the right hand, from the right. But if it just says limit as x approaches some number, then you do both sides. Yep, so good question. Okay, so this question is asking us the limit as x approaches 3. So I didn't plot all the way out to 3. If I had, what do you think, guys? Where is the graph going? What y value is it getting close to as x is getting close to 3? What do you think, Kabir? What do you say? My graph might look like 5, but what should it be? 6. You can also think about plugging the value in. If you have the equation and it's defined and everything works there, you can just look at putting in a 3 would give me a y value of 6. Okay? So the limit as x approaches 3 is 6. Do you see it here? Okay. Without a grid, sometimes it's very easy to get off. Yeah. All right, so let me give you another equation. Let's do my second y here is x plus 3 quantity times x minus 3 over x minus 3. All right, what happens here? Yeah, right? These cancel out and creates a hole. Where is that hole? I know it's when x equals 3, but what's the y value? I'm hearing mumblings of 6. Yes, it is at 6. So if I were to graph this equation, I know I've got a point, and I know I have a hole happening up here. There's my line. Hopefully your line is prettier. Okay, so yes, it is different than the first equation because we do have a hole in our graph. But is the limit different? It's not. Let me show you. So if I draw little people up here, as you are walking along this graph and approaching this x value, as you get right up on the edge of that hole, what is the y value? That's what you're getting really close to. And it's 6. It's totally fine that there's a hole there. People are not falling into the hole. They are going right up to the edge and looking at what y value they're close to. So the limit of this one is also 6. Are we okay with that? There can be a hole and you still have a limit. Okay. All right, so we're going to look at lots of different ways we can find limits, but most of today is going to be about finding them graphically. So you've got this little graph over to the right. Hopefully it's big enough that you guys can see it on your worksheet there. I want you to try to evaluate these limits. So you're looking as x approaches -5, as x approaches 2, as x approaches 0, and as x approaches 4. So go ahead and try to answer those 4 limit questions for me using that graph. Chat with your neighbor. Do you agree? Argue it out if you disagree.
Wait. Well, for C, because it's here and it's here. Yeah, that's why
I don't like this. Yeah. Settle.
Are we debating any of them? C is the troubling one. Yeah. Oh, okay. Okay.
we're not, we don't.
We're not. We're not sure it's right, but we agree.
Yeah.
Okay. Okay. All right, guys. What'd you get for letter A? For letter A? Yes. It's as x approaches -5, so we're looking like over here. It's like you're building a wall at -5 and figuring out like what y value would I run into at that wall. Okay. So it looks like 4. Letter B, as x approaches 2. Now you've got weird stuff. You've got that dot up there. But if you are walking on this graph, what y value are you running into? 3. That dot should not mess with you on your limit, okay? It is 3. Now, what if I had asked you, off to the side here, what if I had said, what is f of 2? Not limits, nothing like that, just what is the function value at 2? 5. Okay, you see the difference. Okay, C, the tricky one. What do you think? Well, is that what the right side would run into? No? Okay.
The right side doesn't go anywhere.
You're right. So this guy, right, he is happily sliding down to 0. This guy is hiking a mountain that looks like it's never going to end. Are your two guys going to run into each other? No. What that means is the limit does not exist. Fan of the movie Mean Girls, that's the whole premise at the end. That's an actual calculus problem. You can just say DNE. A limit does not exist. All right, then letter D should have been a little easier. What'd you get for that one?
0.
0. Okay. So if it's just the general limit and your left and right hand do not match, they don't run into each other, the limit does not exist. Okay. All right, in this big box on your paper here, we're going to talk about those left and right hand limits. So I know it's kind of small on your paper, but hopefully the font is big enough. Do you guys see that tiny little minus sign by the A? Okay, that, it's very small, I know. That is the left hand limit. The negative one means we're coming from the left. So the left hand limit. That is just talking about as your x value approaches A only from the left. That's the only side we care about. So then the second one, when it has a teeny tiny little plus on it, what do you think that means? Yes, the right hand limit. I don't know why I wrote that up. So with these, you just want to pay attention to the notation. Am I asking you for a general limit, or am I asking you for a right or a left-hand limit? Okay. All right. We look at this equation here. We're talking about the absolute value of x over x. We're talking about finding the limit as x approaches 0. So we're going to look at it a couple of ways. I've given you the table. I've given you the graph. One just showing the whole, one not. So first, let's talk about as x approaches 0 from the left. So if I'm going to write on the blank here, the limit of f of x as x approaches 0 from the left would be that little negative. Do you guys see the y value it approaches from the left? As I'm coming along here, if I'm this guy. Hopefully you know your right and left, otherwise this is going to be tricky. What do you think? What y value is it approaching? It's -1. So the left-hand limit is equal to -1. Okay, so then the right-hand limit, I would write that as, squeeze it in here, limit of f of x as x approaches 0 from the right, so with the little plus. What do we think? What is that guy approaching? 1, okay. So did the left and right-hand limits run into each other? Like, were they equivalent? No. So what does that mean about the actual just limit as x approaches 0? Good. You guys are catching on. Does not exist. Okay, so in the little box down here, the limit of f of x as x approaches a equals L if and only if. Do you guys remember that from geometry? Yeah. If the limit of f of x as x approaches a from the left equals L, and the limit of f of x as x approaches a from the right equals L. So that is just simply saying the left hand and right hand limits have to equal each other. Questions so far, guys? Okay. Flip your page. This is the one we're on here. So you've got a graph and you've got 6 limits. Try these 6. Now, again, I know it's small on your paper. Do you guys see on letter A, it says 2 with the little negative sign? Okay, yes. So make sure you see all of those. So go ahead and try to evaluate A through F. Chat with your neighbor. Do you agree? Do you disagree? Yeah. Find someone to compare with.
So I don't know.
You guys agree or disagree? Matthew's like, I don't know. Or which one? D?
Yeah.
Okay.
So if you start going the way left, there's like a little jump to get to it.
So what you're thinking about is like, we'll see if my pen works. Okay, like zoom in on that part and then go from the left. Okay, does that help?
Yeah.
Because yeah, you're not going to start your trek like over here and then be like, you know, walking all the way. That doesn't work. My pen doesn't go. Okay, let's go through them, guys, and see how we did. Letter A, what'd you get? 3. Good. Letter B? 1. So what does that mean for C? Excellent. All right, any questions on those 3? Okay. What about D? 2. E?
2.
Okay, so what does that mean for F? 2. All right, good. You guys didn't let the dot mess with you. It has nothing to do with the limit part of it. Okay? All right, let's stop there for a second. Anybody questions? Any piece of it that you're like, I just don't get why it's 2? Like, is there anything going on? Yeah. For which one? I'm sorry.
Any of the limits, where do you like count out from the edge of the wall?
So, like, as x approaches 5, like, I go over here to an x value of 5. That's where my wall is. And then what I'm thinking about is just approaching it from the right or from the left.
Oh.
You don't start over here and go, oh, it doesn't matter. Because it's only, like, really close to it that we care about. That's what I was doing earlier. You basically, like, you only look at, like, this little part of the graph
Oh.
to figure out the right or left. Does that help?
Yeah.
Okay. Other questions, guys? Anything? Clear it up now, because we're going to keep doing limits. So if you're sitting there wondering something, please ask now, because it's going to keep going up. Okay? All right. So we're also going to talk about continuity today. You understand the general idea of continuity. Like if you have to pick your pencil up when you're drawing a graph, it's not a continuous graph. We have a formal definition of it with very specific ways you have to write whether or not something is continuous. So there's 3 bullet points that you have to go through for a continuity test. The first is that the function is defined at whatever x value you're talking about. The second bullet point is that the limit of the function at that x value exists. And then the third part is that the function value and the limit are the same thing. Okay? So let's go through one here. So we've got our equations. We'll do number 3. Sorry, there's not a lot of room there. F of x equals 1 over 2x plus 1. We want to know, is that continuous at x equals 1/2? So first, we need to figure out what is f of 1/2. Does it even exist? Like, is there a value when I plug in 1/2? So plug it in, and what do you get? One half? Yeah, you get 1/2 when you plug in 1/2. Kind of weird, but yes. So first bullet point, is the function defined at whatever x value we're talking about? Yes, we can check that one off. That is true. Second, is the limit existing at this? So let's think about what this looks like graphically. And I know we don't have a ton of room. I'm going to just draw a tiny little graph right here. Okay, we graphed rational functions earlier in the year. What do you know about this graph? vertical asymptote, horizontal asymptote, any of that stuff?
Both.
What?
Both.
Both? Yes. What are they? You're like, I know there are those things.
This is the one that looks like that.
Yes, it is one that looks like that. Good. Okay, how do we find the vertical asymptote? What, like, determines the vertical asymptote? Not quite.
It's like the denominator to be 0.
Yes, because the asymptote is there because the function doesn't exist at that place. It's giving you, like, the asymptote because it's undefined there. So you're thinking about setting that denominator equal to 0. So where would the asymptote be? Negative 1/2, okay? So somewhere over here. It's bottom heavy, so it has a horizontal asymptote at y equals 0, okay? And then you guys were right with like, oh, the shape is like this thing, right? And this thing. You remember graphing those? Okay. The big concern here, we're talking about what's happening as x approaches 1/2. That is not where the asymptote is. The asymptote is at negative 1/2. The graph is just nice and happy over by 1/2. What would the limit be? And you can't really tell based on my graph. What do you think the limit of this function is as x approaches 1/2? What? It's also 1/2, right? Again, I didn't draw it great. But if you were plotting a point over there, wouldn't you plug in 1/2 and you'd get 1/2 and you can just see that's where the graph is going? Okay. So yes, that limit is also 1/2. Do your first 2 bullet points equal each other? Yes, that means the function is continuous. So your third bullet point is to say f of 1/2 is equal to the limit of f of x as x approaches 1/2. Therefore, which is 3 little dots, f of x is continuous at x equals 1/2. Okay, so all of that is your answer for number 3. Yes. You know, it's obviously a different concept than the IVT, but same idea that, like, go through the bullet points and tell me your conclusion.
So how is it continuous? Like, I know that the way light is going right? But is it saying that because we're looking at x is 1/2, is that why it's continuous? Because if you're looking at something else, would it be like you're
Not
two
continuous.
parts in like the asymptote?
Yes, so that's what we're talking about. We're only asking, is the graph continuous at x equals 1/2? And it is. If I had just asked in general the whole function, you'd say, no, there's an asymptote. Or if I had said, is f of x continuous at x equals negative 1/2? Nope. You know, we've got an asymptote there. You know it's not continuous. You have to explain why in the bullet points, but you know visually that's not a continuous function. Okay. Yeah?
So to find, like, if the limit of f of x, a limit of x approaches 1/2, just plug it into the original equation.
Yes, and that's what, if you have the graph, you can obviously just do it graphically. If you only have the equation, you can plug it in. If it's undefined, then there's other ways you have to go about doing it, and that's more of what lesson 10.2 is going to be. But if you can plug it in and you get a value, that's the limit, and it's very simple. Okay? All right, let's look at number 4. So our first bullet point, well, first I should have asked you a question about this. Where am I asking you if this is continuous? So is g of x continuous at x equals 0? There's your question for 4. So what's the first thing we're looking for? F of 0, right? Is the function value at that point a thing? Like, does it exist? Yeah, it's a piecewise. So first you're like, oh, could it be different things? Well, which one would you actually plug 0 into? None of them, right? Do either of them say or equal to 0? No, they're both open circles. So does f of 0 exist? No, f of 0 does not exist. Exactly, yes. Woo! Much happier. We like it when they're not continuous. Therefore, f of x. Oh, I guess it was g of x this time. Sorry. I changed letters. And again, we'd say is not continuous at x equals 0. It's continuous in other places, but not there. Okay, so that whole thing is your answer for 4. All right. Number 5. Again, I didn't ask you where this one was continuous. Is h of x continuous at x equals 0? You guys try this one. See if you can get through your bullet points and determine whether or not it's continuous. Give me a minute.
So, use the next less than a top. Yeah.
I don't know. I thought you put in the 0, but I'm not. Because I do remember how there's that's right.
When you're doing question 5, the second bullet point, do you plug in 0 or do you plug in -1?
So I'm asking you, is it continuous at 0?
So you plug in 0.
Yes.
So won't the first bullet point is true, point isn't always true?
So not necessarily, and you'd see it more. And you can see it every once in a while algebraically, but a lot of times you'd see it graphically. So like, let's say, back to that. Does the function exist? Yeah, you've got a function value, you've got a limit, but they're different. Okay. Talk to each other, guys. See if you agree on your bullet points.
Wait. So how do you see that algebraically? Because like if you were
So what if I gave you like a piecewise? Oops. It was like. And I said this happens when x is less than. Well, we'll even do it this way. This is when x is not equal to 4 And this is when x equals 4. So like graphing it, you'd have this line everywhere except at 4, you'd have that y value of 3. Otherwise, here. Do you see what I mean? Like you'd have this and like a whole, yeah. I've made up bad numbers, but do you get the idea? Okay. But most of the time those show up graphically. All right, so let's go through the steps of it. Is it continuous at x equals 0? So first, what is h of 0? -1, good. Okay. Limit of h of x as x approaches 0. -1, right? It's still the same thing. So third one, h of 0 equals the limit of h of x as x approaches 0. Therefore, h of x is continuous at x equals 0. How do we do? Good? Fantastic. Okay. All right, questions? Give you a second, make sure everybody's got it jotted down. All right, guys, turn the page. Okay, so just a quick review of the different types of discontinuity. First one is infinite. What else might we call that? Do you guys remember? No graph? No? What part of a graph is infinite? Let me draw a picture for you, and then I'm sure you will have it. Okay, good job. All right. So infinite discontinuity, that is the same as an asymptote. And this happens where the denominator equals 0. All right, guys, removable. What's another name for removable? Yes, that is a hole. Good job. So you might have a graph. It's got a hole. I drew a really messy hole. Same as a hole. Do you remember how that happens? Like algebraically, what's going on to create the hole? Yeah, same factor. So look for a common factor. Numerator and denominator. Okay, a jump doesn't really have another name, it just is. You often see it in what kind of equations? Piecewise, good. Very frequently in piecewise. And with a jump, the left-hand limit does not equal the right-hand limit. All right, we're gonna see. Oh, go ahead.
Is the piecewise function the only time you see a jump?
I mean, so I guess like the equation we looked at initially, if it's absolute value of x over x, like that graph looks like that. So technically that has a jump, but most of the time it's going to be from a piecewise. All right, we're going to skip number 6 because I don't think you need another one with the bullet points. Am I right that we're doing okay with the idea of the bullet points? Okay, so let's look at 7 and 8. All right, I want you to find the value of k so that the functions are continuous, which means we've got piecewise functions here. You need the right and the left-hand limits to be the same for it to be continuous. You essentially need your two pieces to run into each other. We've graphed those before, right? Where you go and you graph it and you're like, oh, I had an open circle here going this way, and then it got filled in by that graph going that way. That's a continuous function. Okay, so that's what you're trying to figure out. So I'll give you a minute here. Try just number 7 first. Can you figure out what k is so that these two, or that this function is a continuous function? So try 7. Chat with each other, see if you got the same k value. Oh, and guys, it's not really, I mean, it kind of matters, but there should have been a not equals through this. Otherwise, your notation doesn't actually make sense. This one is that. Yeah. Otherwise, you're like, what? It's the same for both. Yes, so sorry. That should be there. And you should end up with just a nice integer for your k. All right, guys, what'd you get for k? -1 is correct. Okay, let's go through it. So if it's going to be continuous, that means the two graphs have to run into each other. They run into each other by having the same y value. Okay, so I know for this first one, I can plug in the -2. I understand it says that's when x does not equal -2, but as far as finding the limit and it being continuous and running into each other, you have to plug in that x value. This is the only x value we care about, okay? So I'm going to plug in -2. So I have -2 squared plus 5 times -2 plus 6 over -2 squared plus 3 times -2 plus 2. So I have 4 minus 10. Oh, I should have factored. Sorry, guys. Let's start over. Like, I'm getting 0. X plus 3, x plus 2, x plus 1, x plus 2. Okay. So clearly this is not continuous for all values. But if we're talking about at x equals -2, we can still figure it out. So I plug in the -2. -2 plus 3 over -2 plus 1. I get -1. Okay. That is what this k has to equal. If there had been an x involved in that equation, you'd also have to plug in the -2 for the x's and then solve for k. There's no x happening there. It's just a constant value. So k has to equal -1. That's the only way that this graph can be continuous at x equals -2. Again, I get it. It's discontinuous other places. There's holes. There's other things happening with that top function. But for them to be equal at -2 or continuous at -2, k equals -1. Are we okay with it? Yeah.
Okay. So when, like, why did you plug in -2? Because, like, I did it because it was the whole.
Mm-hmm.
But so why did you just because?
So if I'm graphing this, like anything that I'm graphing, if I'm talking about it being continuous at this x value of -2, and that's because that's where the two pieces happen. I can see one of them, and I'm not going to draw this correctly. Pretend that one of them, is doing this. I need to know, does the other one fill that in? Okay? And the only way I can do that is by using this x value. So that's why I did it. Okay? All right. Try number 8. Same idea. You're finding k. I want you to make it continuous at x equals 4. So again, you've got two pieces. You need those pieces to run into each other. You need one of them to like fill in the hole of the other one so that it's a continuous function. Try it out. Once you've got a k value, talk to each other. Good start. Good start. Plug in 4 for x. I like it.
Will you equal that equation?
Well, if you need these two to run into each other, right? Equal them to each other.
So much fun.
You might get more than one answer.
So we love
Yes.
it. What's 48 times 4?
192.
It is 192. Good job. You could always do 50 times 4 and then subtract 2 times 4.
Just can't do it. Don't have the brain.
192. Is that what you're looking at? Or are you trying to factor 192 now?
Oh,
okay.
That too.
Like, oh no, now what do I do with 192? Yeah, it's
96. But that is not helpful.
yeah, you need to get to like 4. So you want numbers that are fairly close to each other to multiply to give you 192.
I like just keep like
You're like,
I can multiply, but I cannot factor.
I can't factor if I have a calculator, then I can just plug in.
wow! You can do it. You can write stuff down if you're stuck.
Let's try divided by.
I already have all of this written.
You know that it was 4 times 48, so you got a lot of like 4s happening in this, right? Because 48 has a lot of multiples of 4.
14, 192.
No, 196.
I'm trying to.
But you probably want numbers kind of close to that.
Yep. Yes. I just can't lie.
So cclearly the factoring that's the struggle for us today. See, writing stuff down, it works. Okay, let's go through it. Well, first, did anybody get 2 answers?
I did.
What do we got?
16 and 12.
One of them's negative. Which one? Negative 12. There we go. Okay. The way you find this, you're plugging the 4 in for the x, and you're setting the 2 pieces equal to each other. You need them to be equal because they have to run into each other.
I love multiplication. It's not
This
just
calculate.
Oh dear.
if I could do all the for everything in my life, I would do it.
You'd be good. Okay. All right, guys. Questions on that? You get the idea of how you approach that type of problem? Okay.
Now I do.
All right. Let's keep going. Our notes are clearly a little long today.
Times 50. How much homework?
I know you're not going to really get your homework done in class.
Yeah.
All right, guys. We're also going to talk about unbounded or infinite limits, meaning there's an asymptote and you're approaching that asymptote. So let's look at this graph down here. I gave you the limit as x approaches 3 of x plus 2 over x minus 3. So this is what the graph looks like for x plus 2 over x minus 3. Okay, it's a vertical asymptote at 3. It's a horizontal asymptote at 1. That should be familiar to you from graphing rational functions. So the left-hand limit. So as I come from the left side, in other words, we're doing, you know, as x approaches 3 from the left, where is my guy going? Negative infinity. Okay. We're also going to add to that does not exist. So different textbooks, you're going to see different notations. Some will just say negative infinity. Some will include the does not exist. The reason I like to include it is because is infinity a value, a defined value? No. So I like to say, like, okay, no, we know the direction we're going, but that's not truly the limit. Okay? So what about the right-hand limit? What would we say for that one? Yep, infinity does not exist. Okay, so again, you're telling me the direction, but like, hey, I know that's not actually a number. Okay, and that was again as x approached 3 from the right. So what do you think just the general limit as x approaches 3? Does not exist. I know I asked you, does it exist? No, it does not exist. Now, if they had both been going the same direction, like say you had an asymptote and both sides went to infinity, then again, I'd like you to say infinity, comma, does not exist. Like, we know they both go the same direction, but that's not actually.
Wait, where did you get the infinity values from?
So, like the right-hand one. So here's my guy, right? He's approaching 3. There's an asymptote there.
Oh, so just never.
So he's gonna, man, that's gonna be a climb. He's got some hiking ahead of him, okay? All right. I don't know why this is written in such large font for you, but here it is. Yes, then. So, and we've talked about this many times already. The left-hand limit, if that equals the right-hand limit, then that overall limit will exist and is whatever that value was for the left-hand limit. Okay? Questions? Keep going. Yeah, well, there's just kind of weird spacing on some of the pages, too. All right, you guys try this one. So this time we've got the function 1 over x squared. There's what the graph looks like. Tell me the left hand, right hand, and then let's just say, not does it exist, but just evaluate the overall limit there at the bottom, okay?
This is yes, yes. Yes.
I know, they want to meet up, but they just don't. All right, guys, so what's the left-hand limit? All right, what about the right-hand limit? Yep. And then the overall limit. Well, are they going the same direction? The left and right, you said they want to meet, right? So they're both heading the same way. So tell me that. Tell me like, hey, we know it's going towards infinity, but really it still does not exist. Okay? Does that make sense?
That goes against this big gold box.
Well, aren't the left hand and the right hand the same thing?
Exactly. Yeah. So shouldn't there be a common limit?
Right. It's the same thing I wrote for the left and the right hand. Do you see it?
Oh, yeah.
Okay. I'm like, yes, I agree with you. All right, questions on that one? The infinity ones are a little weird. Okay. We'll look at this one. It's kind of a weird equation. So your function is x minus cosine of x over 1,000. Super common equation we use all the time, right? Yeah. So the graph of it looks like the limit would be 0, right? Okay, if you look at the table of values, though, and go a little closer, it's not. I know your table's small. As you approach 0 from either side, what are your y values getting close to? And really, what just does the y value equal when x is 0? Yeah, so that is the limit. It's negative 0.001. So again, that's one where you wouldn't even actually need the graph. You could just plug in 0 into that equation. You'd have 0 minus the cosine of 0 over 1,000. Well, what's the cosine of 0? So this is really negative 1 over 1,000, which is negative 0.001. Okay? And again, we'll do a lot more algebraic evaluating next time. All right, now we've got another weird one. The limit as x approaches 0 for the sine of 1 over x. So I've given you the table, and I've given you the graph of this. The table you can see at 0 is error because we can't do 1 divided by 0. But if you look at the y values as you're getting close to that, you know, the x values are approaching it. Are your y values actually similar on either side? Not really, right? Like the graph, you'd look at that graph and go, I don't know, it's probably 0. It's actually not. It's going positive to negative. It's doing weird things. This is called an oscillation. It's a graph that oscillates back and forth and isn't like settling in on a value for you to find the limit. It's oscillating so wildly that there's not a single limit. So when you have a wild oscillation, the limit does not exist. Okay? So we're going to list out when a limit does not exist. That's one. It's the least common of the ones you're going to see, so I'll put that third. The function oscillates wildly. That is a case where the limit does not exist. Can you think of the other two ways that a limit does not exist? Yep. Can you think of the third one? It's a little trickier to put in words. Yeah. So, yes, but that's going to come into play more with the left and right hand limit. But are you thinking about the ones that approached infinity? Sure. Yeah, we'll go with those. Yes. When it doesn't approach a defined value. So if the function does not approach like a finite, an actual numerical value. So all the ones where we wrote infinity, comma, does not exist. That's what we're talking about here. All right, are we okay with those three? Excellent. All right, I want you to try again from the graph here, A through I. Now, I will tell you the weird graph here, all of this stuff, this is supposed to be oscillating wildly, all of that, okay? If that helps you. It looks like it ends up at a nice happy value, but it's oscillating wildly. Okay. So B might be a little tricky. Yeah, if you can't read something, let me know. I know the font is tiny for you. Is that a funny bone to hit? All right, guys, talk to your neighbors when you're done. Find someone to compare with. Do you agree? Jeff, you want to shut the laptop? Thank you. you.
Oh. I'm so right.
You're from the right. We're from the left. Wait,
Yeah, it's the other one.
Do we know our rights and lefts?
apparently not.
Apparently, that's tricky.
It's the other Yes. Oh, yeah.
I think that's one is just like a singular.
Oh.
That is kind of
Oh, I went this.
So I have 0.
All right, guys. Letter A, what'd you get? 0. Okay, B, what'd you get? Okay, yeah, remember this is oscillating wildly. Does not exist. Yep, scribbling is oscillating wildly. Okay, so what does that mean for C? Okay, that one you probably got right. All right, letter D. 3, letter E. 0, and F. Good. Letter G. H. I. Okay, good job. So we're pretty good graphically, unless it's oscillating wildly and you can't tell. Other than that, we're doing okay. All right. We're gonna jump around just a little bit here. Okay, let's go to number 6. So we're gonna skip 5. Yeah, go ahead. Go to this piecewise one here. So find the limit as x approaches 2, and then you're given this piecewise function. So when we're evaluating just the overall limit, we need to look at the right-hand limit and the left-hand limit. Do I necessarily care about what is happening exactly at x equals 2? No. So I can ignore this. It does not matter. But what do I need to be true about these two if the limit's going to exist? Yeah, you have to evaluate the limit for both of those. Basically, plug in the 2 for both of them and see, are they the same thing? Okay? So you're technically doing the limit of f of x as x approaches 2 from the left, which is the top one from the left, or is the bottom one from the left? Top one, right? X is less than 2. That thing's on the left side of it. Okay, that's from the left. So what I'm doing is just plugging a 2 in. So what do I get? 7. So that's the left-hand limit. Robert, put your phone away for me. Thank you. All right, so then I need to evaluate that limit. So the limit of f of x as x approaches 2 from the right. So does everybody see that's the bottom piece there? The x is greater than 2. That's stuff on the right of 2. So I'd plug the 2 in there. So 2 squared plus 3. What do I get? 7. Did your left and right-hand limits equal each other? Yes. So then you can say the limit of f of x as x approaches 2 is 7. We okay there? The more comfortable you can get with piecewise functions and what's happening left and right and graphically, all of it, it's going to help you. Okay, number 7, we've got sometimes, always, and never. You remember those from geometry? Maybe you blocked them out, I don't know. All right, so if the limit as x approaches 2 of f of x does not exist, then the limit as x approaches 2 from the right for f of x does not exist. Sometimes, right? Good. It may very well be that the right-hand limit exists, but is not equal to the left-hand limit. So then the overall limit would not exist. All right, what about B? If the limit from the right does not exist, then just the general limit does not exist. Always, yeah. Okay. We okay with this? All right, number 8. So we're going to find the limit as x approaches 3 from the right and 3 from the left for this equation, 2 over x minus 3. What does this graph look like? It's got an asymptote. Where is the asymptote? 3. Okay, we got a vertical asymptote at 3. Is it going something like this? Yeah, okay. Do we need like a perfectly graphed graph here? No, we need to know what is it approaching when x approaches 3 from the right and 3 from the left. So what would you say for the limit as x approaches 3 from the right? Yes, good. And what about 3 from the left? Exactly. Okay. Tell me the direction it's going, but hey, it really doesn't exist. Okay. All right. Last thing, guys. One more graph for you guys to evaluate some limits. I think this is your last thing. Yes. Okay. All right. A through I. Give it a try. An interesting graph. And I know there's not arrows on this graph, but realize like where the asymptotes are, like these graphs are continuing like up or down. Once you've got them, check with someone. Do you agree? Check with each other. Give me one more minute, guys, then we'll go through them.
I had positive in that too, but I wasn't sure if I was able to do both. For C and D is positive, right? That's what I had in grade 6. Zero.
Okay, because that is the
Yeah, it's kind of weird.
And then for G and H.
Zero from the left.
Oh, and then for the right, it's infinity. The normal one is doesn't exist.
Okay, guys, let's go through them. All right, so letter A, what did you get? 1. Okay, letter B then is down, so let's go down. What'd you get for B? Yeah, infinity and does not exist. What about for C? Yes. Good. What about D? Getting a lot of these. Yes, infinity does not exist. What about, I guess, E, back up to the top here. We're going in a weird order. They are labeled strangely. Okay, it does not exist. What about F? Good. G? H? And I? 0. Okay. Yes. All right, guys, how'd we do?
Okay.
Limits aren't too bad, right? They're fun, yeah. Look at that. Calculus is fun. All right, guys, so you do have a math-based homework. It's been a while since you've had a math-based homework, so when is it due?
Thursday at 5.
Tomorrow night at 11:59, yes. Okay.
Is this like all math space next again?
No, it'll be a, you're not going to have any more of those. Combo.
Exactly what you do on your homework is on the test.